Well, hey everybody, welcome back to PreCalculus. This is day 6. We're going to talk about function properties. Remember on day 5 we talked about lines, and then on day 4 we talked about relations and functions. And again, so today is going to be all about more on functions. So let's start with a definition. And we're actually going to give a definition of the graph of a function. So the graph of a function f is the following set of points. And so this is the set of all ordered pairs of the form x comma f of x such that x is in the domain of the function f. So for example, so we're going to say the graph of the function f of x equals 2x plus 1. It's going to be a set of points. So yeah, the graph of f of x equals 2x plus 1 is the set of points. So it's the set of all x comma, well, what's the y value? The y value is 2x plus 1. So that really is x comma y, such that x is in the domain of f. Well, what is the domain of f? Remember, the domain is the set of all legal inputs. So x is real because the set of all inputs, or the domain of the function, would be the set of all real numbers. So this collection of points, this actually is the graph. No, I know that you're used to thinking about the graph like this, but really we talk about in math, the graph is a set of points. That might be new for you. I remember when I was a student thinking that was quite strange, but as you develop more tools to deal with sets in set theory, it actually makes sense to define it in this way. So that's what f of x equals 2x plus 1. So yeah, we think of the graph like this, but truly the graph is the collection of all points of this form. Okay, so now we want to develop a test to determine if a relation is a function. So this is going to be the classic vertical line test. And it says the following. So a set of points in R2 is the graph of y as a function. So is the graph of y as a function of f or function of x if and only if every vertical line intersects the graph of f at most one time. Okay, so yeah, a set of points in R2 is the graph of y as a function of x. So this is a function test. So yeah, a set of points in R2 is the graph of y as a function of x if and only if every vertical line intersects the graph of f at most one time. So let's see some examples of that. So for example, let's consider the following. Okay, so let's say I have the following. So here's f of x. And notice, no matter how I construct a vertical line, so whether I do that here, or here, or here, or here, or here, notice that that vertical line intersects the graph at most one time. So since any vertical line I draw intersects the graph at most once, y is a function of x. Let's actually say that. So we'll say, yeah, y is a function of x since every vertical line intersects the graph at most once. Okay, so yeah, so that's how I can determine. So for any vertical line that I draw, that vertical line intersects the graph at most one time. Let's look at maybe a circle. And let's say maybe this is the, what we call in math, the unit circle. Well, here we don't have a function. Why is that? Because there exists at least one vertical line such that when I intersect it with the graph, I get multiple intersection points. So I'm going to say, well, y is not a function of x, as there exists, that means there's at least one, so there exists a vertical line that intersects the graph in more than one location. So you can see that here and here. So in terms of the definition of a function, what's happening here is that you have a particular x value mapping to multiple y values or multiple outputs. So that's the issue. So maybe if this is x1 and this is, I don't know, y1 and y2, if you sort of looked at a little chart like this, you can see that this maps here, but also here. By definition of function, every value in the domain would need to get to mapped to one unique location. And so that's not mapped or sent to one unique location, so not a function. So next we want to discuss the zeros of a function. And so of course we want to give a definition. So the zeros of f of x are the x values for which f of x equals 0. So let's actually say that. So the zeros of f of x are the x values for which f of x equals 0. So this is a big idea in math. So the zeros are all the values, all the x's that the function sends to 0. So for example, if I had this graph, these would be the zeros. These are the x values that produce an output or a y value of 0. Okay, so in this case, I would say that x1 is a 0 and x2 is a 0. Again, why is that? Let's see. Well, x1 is a 0 since f of, or the corresponding output or y value, f of x1 is equal to 0. And then similarly, x2 is a 0 for the same reason, since f of x2 equals 0. That's the x value that the function sends to 0. So next goal. So how do we find zeros algebraically? So geometrically, we can just look at the picture and say, oh, maybe I've got one here and here, but how do we find zeros algebraically? Well, it's right in the definition. It looks like we should solve this equation. So we solve f of x equals 0 for all x's. So let's try this out. Let's take this idea for a test spin. So, for example, I'm going to say find the zeros of the following functions. Okay, so let's say the first function is f of x equals 3x minus 1. Let's say the second function is, let's say g of x equals 16x squared minus x cubed. Let's say the next function is maybe f of x equals 5x plus 9 over x minus 2. And let's say the last function is, let's say g of x equals 3x squared plus x minus 10. So essentially we have 4 examples that we're doing. But for each of these, we want to find the zeros. Okay, so for the first one. So the key really is just to use the definition. So we want to find the zeros of f of x equals 3x minus 1. So that means that we want to solve f of x equals 0. And so we want f of x equal to 0. And then to solve this algebraically, that's not bad at all. We're going to add 1 to both sides. That's going to leave us with 3x equals 1. And then we'll divide both sides by 3. And of course, we could check this. So we have x equals 1/3 is a 0 of the function f of x equals 3x minus 1. Okay, so we check So let's compute f of 1/3. If we did this correctly, we should get 0 as an output. So we've got 3 times a third, but a third of 3 is just 1 minus 1, and that equals 0. So therefore, x equals 1/3 is a 0 of the function. What does that mean geometrically? And that's an x value where the graph crosses through the x-axis. So another way to think about this is the x-intercept. It turns out that the idea of a 0 is a little bit more general than an x-intercept. We'll see that when we study polynomials. But for now, that's a decent way to think about it. All right, let's try the next one. Okay, so we want to find the zeros of g of x. So we want to solve this for x. So we've got 16x squared minus x cubed is equal to 0. We're going to factor out the greatest common factor. That's x squared. That leaves me with 16 minus x. And remember, if the product of two things is equal to 0, then at least one of them is 0. That allows me to do this. And so here x is 0 and x is 16. So there's two zeros. There's two inputs that the function g will send to 0 as an output. Okay, so we can easily check this. So we'll check g of 0. That's equal to 16 times 0 squared minus 0 cubed. But that's exactly 0 minus 0, which is 0. So therefore, x equals 0 is a 0 of the function. And then we'll check x equals 16. So this is 16 times 16 squared minus 16 cubed. But if I look at the exponents here, that's the same thing as 16 cubed, right? Minus 16 cubed, and any number minus itself is 0. So that checks. So let's try the next one. So this one looks a little tougher than the others, but common theme in mathematics is just follow the definition. So we want to solve this for x. So how do I solve fraction equals 0? We could just put the 0 over 1 and cross multiply. So this product is equal to this product. Another thing to do would be to multiply both sides by x minus 2 to get rid of the fraction. You get the same thing either way. Okay, so we subtract 9 from both sides. So we've got 5x is equal to minus 9. And then we divide both sides by 5. And so x is negative 9/5. So that's my 0 of the function. Notice that 2 is not a 0. 2 is the value that makes the function undefined. The 0 is negative 9/5. And I'll leave the check as an exercise. And then let's try part D. Okay, so we want to solve this equation for x. Okay, so I think we should try and factor this. So we'll try 3x and x. Let's try minus 5 and plus 2. Let's just check this. This product is this. The product of the outers plus the inners is this. So this product plus this product is this. And then this product, the product of the outers. I'm sorry, the product of the lasts is this. So that's a good factorization. And we know if the product of two things is 0, then at least one of the factors is 0. Add 5 to both sides. And then divide by 3. So x is equal to 5/3. That's a 0 of the function. And x equals -2 is the other 0 of the function. Okay, so the next concept we want to talk about is this idea of increasing, decreasing, or a function being constant. So these 3 ideas. So in terms of a picture, what do I mean by increasing? What do I mean by decreasing? What do I mean by a function being constant? Well, let's look at the picture and then we'll try to get a formal definition out of this. So a function's increasing might look like this. If a function's constant, it might look like this. And a function is decreasing, might look like this. Okay, so on some interval here, and we'll call this x1, we'll call this x2. So from -infinity to x1, looks like my function is increasing. And then here, this should be parallel to the x-axis. Can I fix it? I think we're okay. Imagine that's parallel to the x-axis, so that should be constant. That gets a smiley face. There we go. And then here we're decreasing from x2 to infinity. Okay, so how do I say this in... actually, let's say from A to B, because I want to use x1 and x2. Let's do this. We don't lose anything from doing that. Let's say that's A to B. That gets another smiley face. Look at that. That's my get out of jail free card, the smiley face. Okay, so let's define this formally. So 1, a function f is increasing on an interval I if for any x1 and x2 and I, x1 strictly less than x2 implies f of x1 is less than f of x2. Okay, so what does that mean in a picture? So let's say it again. And so a function f is increasing on an interval I if for any x1 and x2 in the interval I, this inequality implies this inequality. Okay, so let's see how that gives us increasing. So let's say here's x1, let's say here's x2. And then we want the corresponding y values, right? F of. So f of x1, let's say that's here. F of x2 is here. And yeah, my function is increasing. So yeah, so if x1 is less than x2, that implies that f of x1 is less than f of x2, then my function is increasing. Okay, so yeah, x1 less than x2 implies f of x1 is less than f of x2. Then f is increasing on I. What about decreasing? What if I wanted to go this way? Can you think about what would need to happen? I'd still want to keep this ordering, but this ordering would switch. So let's say that. So 2, a function f is decreasing on an interval I. If for any x1, x2, and I, x1 strictly less than x2 implies that f of x1 is strictly greater than f of x2. So x1 strictly less than x2. Implies that f of x1 is strictly larger than f of x2. And that makes sense. So this captures the notion of a function decreasing. What about the idea of a function being constant? Well, we're going to say a function f is constant on an interval if for any x1 and x2 in the interval, so if for any x1 and x2 in the interval, we have that f of x1 is equal to f of x2. And let's see why that makes sense. Why does that describe a function being constant? Well, here these line up with the same y value, so that means that f of x1, that's the y value that x1 is sent to, is the same thing as f of x2, that's the y value that x2 is sent to. So that makes sense as a definition. Okay, so let's look at the graph of a function and see if we can determine where it's increasing, decreasing, and maybe constant. Might not be constant. Might only have one of these properties. Let's see if we can determine. Okay, so for example, let's consider f of x equals 3x squared minus x cubed. And we want to determine the intervals on which f is increasing, decreasing, and constant. And of course, we're reading from left to right. Okay, so let's take a look. It looks like the graph of f is decreasing from minus infinity until 0. So we're decreasing. Again, reading from left to right. So I'm describing this in terms of x values, not y values, right? So I'm decreasing from minus infinity to 0. And then it looks like I'm increasing from 0 until maybe 2. So I'm sort of guessing here. So increasing to about 2. Right? There's where it seems to stop. And then I start decreasing again. So it looks like I'm decreasing from 2 to infinity. And as you can see, the function's not constant. Okay, so let's talk about the idea of average rate of change. We mentioned this before with lines, but now we can talk about it a little bit more generally. And so let's give the definition. So we say the average rate of change between any 2 points let's call those points x1 comma f of x1, right? The x value and the corresponding y value. And let's call the other point x2 comma f of x2. So the average rate of change between any 2 points x1 comma f of x1 and x2 comma f of x2 is the slope of the line connecting the 2 points. And the line connecting these 2 points, that's called the secant line. So for example, say I had the following function f of x, and let's say here is x1, let's say here's x2, right here would be f of x1, right, the y value, that would be f of x1, and then the y value here would be f of x2, and then the slope of this line connecting them, that would be the average rate of change from x1 to x2. So let's actually say that. So the average rate of change from x1 to x2 is, I'm going to say it's the slope of the secant line, and that would be the change in y's, so f of x2 minus f of x1 over the change in x's. And so let's do an example where we find the average rate of change. Okay, so yeah, for example, say find the average rate of change of the function f of x equals x squared minus 2x plus 8 from x1 equals 1 to x2 equals 5. And so we know that the average rate of change is equal to the slope of the secant line, and that's equal to f of x2 minus f of x1 over x2 minus x1. Okay, so what does that mean? Well, it means that I want f of 5 minus, because 5 is x2, right? So f of 5 minus f of 1 over 5 minus 1. Does it remind you of the difference quotient from before? It should. Most certainly should. So what is f of 5? It's our function evaluated at 5. So plug 5 in for all the x's to find f of 5. So that's f of 5 minus f of 1. And we know to find f of 1, we plug 1 in for all the x's. So like this. And that's over 5 minus 1, which is 4. So this looks like 25 minus 10 plus 8 when I compute. And that looks like minus 1. So just distributing the negative here. So plus 2 minus 8. All over 4. But that looks like 16/4. And so that's exactly 4. So 4 is the average rate of change from x1 equals 1 to x2 equals 5. Could be feet per second, miles per hour, could be dollars per year, whatever the context is in your problem. So just quickly, suppose we had the following context. So I want to do sort of a different example where maybe we don't do a computation, we just think about this for a second. And let's say that this t-axis represents time in seconds. And let's say this s-axis represents distance in feet. And let's say I've got some function here. And let's say here is t1, and let's say here is t2. And say here's the secant line, the line that connects the 2 points. Well, the slope of this would give you your average speed, right? Feet per second. So just as an application. So your average speed would be equal to s of t2 minus s of t1 over t2 minus t1. And that, of course, would be feet, because the s's describe feet, per, because out of, divided by, second. So that would be your average speed from this time to this time. All right, so the next thing we want to develop is this so-called library of functions. So yeah, we want to amass a library of functions because we want to perform some transformations on them coming up. So we want to understand how transformations work on really common and familiar graphs. That'll give us a lot of flexibility in the future. So first in our library is a constant function. And so that might be y equals c, or f of x equals c, where c is a real number. And that might look like this. So let's say here c. This is the line y equals c, or f of x equals c. And we want to note some important features like the domain. And I'll start to talk about the range. So the domain, that's the set of all inputs that keep the function defined. Well, what am I allowed to plug in here? I can plug in any number I like, and I always get the same output. So yeah, you pick any real number, plug it in, and the output is always that constant. So the domain in interval notation is the set of real numbers. Now the range, that's the set of outputs. So the range, what are my outputs? There's only a single output, so the range R is equal to the singleton set of C, because this constant function only outputs one y value. It outputs the y value C. So let's also note, is there any important symmetry? Well, it looks like there's y-axis symmetry. And what about increasing, decreasing, and constant? Well, this function, of course, is constant on the interval minus infinity to infinity. Okay, so that's our first function in our library. So, for example, if I get something like, f of x equals 10, you know what that looks like. F of x equals -7, right? This just sort of shifts depending on this number. Next is the so-called identity function. And that's f of x equals x, also known as y equals x. And so we know what this looks like. So this is the line that will bisect quadrants 1 and 3. And so let's note the domain. Well, the domain is the set of real numbers. You can plug in any real number you like, and the function's defined. You can also think about the domain geometrically. As I sweep my hand along this way, horizontally, for which x values do I bump into graph? Every x value. Now the range is a set of outputs. And so which values do I output? It looks like I output every real number. If I want to think about this geometrically, if I sweep my hand this way, where do I bump into graph? Well, for every real number, I bump into graph. And what about symmetry? Looks like there's origin symmetry. If I have a point here, its image is over here through the origin. And that's true for any point. And it looks like if I move from left to right, this is increasing on the interval minus infinity to infinity. Super, super classic function. Okay, so next let's talk about the absolute value function. Very, very important function. And so this is f of x equals the absolute value of x. And I want you to recall the definition of the absolute value. That's important to know. the absolute value of x is equal to x exactly when x is non-negative, and the absolute value of x is equal to minus x for values of x that are negative. Well, by this definition, if I'm at 0 or to the right of 0, I'm going to see y equals x. And if I'm to the left of 0, I see the graph y equals minus x. So that's the graph of the absolute value function. And so, of course, let's note the domain, the range, the symmetry, and increasing, decreasing. So domain, that's the set of all real numbers. You can plug in any real number you like, and there'll be a meaningful output. Another way to think about it is as I sweep my hand along this way, where do I bump into graph? For every x. Okay, the range, that's the set of outputs. Well, I'm certainly not going to output any negative numbers here. So the range is a set of non-negative real numbers. And again, if I think about this geometrically, as I sweep my hand this way, where do I bump into graph? From y equals 0 on. And this graph has y-axis symmetry. Okay, what about increasing, decreasing? Well, it looks like this function is decreasing from negative infinity to 0. And increasing on the interval 0 to infinity. So next up is another classic. Next is a standard quadratic. And so this is f of x equals x squared. So it's sort of a classic parabola with its vertex at the origin. It's got this smiley concave upward shape. And so of course we can give the domain and the range. So domain, if I sweep my hand this way, eventually, because this will spread out forever, I will bump into all real numbers. Another way to think about this, remember the domain is the set of all inputs that produce a legal output. And for any real number I choose, I'll get some output. So that'll be defined for every real number input. Now the range is from 0 to infinity. I think, what kind of numbers are you going to output? Well, I'm certainly not going to output any negative numbers. And so the smallest real number that I'll output is 0, and then I'll output every real number after that. Or if I go this way, I bump into graph from y equals 0 on. This, of course, has y-axis symmetry. And this is decreasing. On the interval minus infinity to 0. And it's increasing on the interval 0 to infinity. Okay, so next we want to talk about the cubic function. I think, was that 4 or 5? That was 4. This is 5. That's live math for you, folks. That's what you get. That gets a smiley face. Okay, so for 5, we got this cubic function, or standard cubic function. And so this is f of x equals x cubed. Okay, so it has this shape. And of course, we want the domain, we want the range, etc. So the domain. You're probably seeing this is the set of all real numbers, or it's the interval from minus infinity to infinity. And the range, well, that's also going to be minus infinity to infinity. So domain, because I'll bump into graph everywhere if I go this way. And range makes sense because I'll bump into graph for every real number y, I'll bump into graph. And what about symmetry? This has origin symmetry. So yeah, if I pick a point and I reflect it through the origin, the image will be on the graph down here. And it looks like this is forever increasing. So this is increasing on the interval minus infinity to infinity. So the next will be our reciprocal function. And so what do I mean by reciprocal? Well, it's just the reciprocal or the flip of x, so it's 1 over x. Okay, so it looks like this. And so of course we want the domain. It looks like I'm going to bump into graph everywhere except for one spot. So it looks like x equals 0 is problematic. It makes sense because I don't want to divide by 0. So I want to delete 0. That's how we delete 0 in terms of interval notation. And then I think the range has a similar omission of 0. And this has origin symmetry, where if I pick any point and I look at its reflection through the origin, its image will be on the graph over here. And I notice that this graph is decreasing from minus infinity to 0, and then again from 0 to infinity. So next one, I don't have a nice name for this one. We can call it Ralph. Or Bob. Or she. Or Juniper. You can call it whatever you want. But I don't know a name for this. So what does Ralph look like? I remember when I was a student, I used to call this the volcano function. So it looks like this. It should be symmetric about the y-axis. So let's give the domain of Ralph. So domain looks like minus infinity to 0, union 0 to infinity. And what about the range? The range of Ralph. Well, I think from 0 to infinity, not including 0, of course. And symmetry, if I drew this correctly, it should have y-axis symmetry. And what about increasing, decreasing? So Ralph is increasing from minus infinity to 0, and Ralph is decreasing from 0 to infinity. Okay, so our next function is going to be the square root function. So this is a classic. So this is f of x equals the square root of x. Looks like this. And so of course we want to give the domain. So interval from 0 to infinity inclusive of 0. What about the range? Looks like the range is actually the same as the domain in this case. And there's no symmetry that we care about, right? So this doesn't have a type of symmetry that we're interested in. So this has no symmetry. But what about increasing, decreasing? Well, this is increasing on the interval 0 inclusive of 0 to infinity. And then lastly, I want to talk about quite a special function. And so this one we're going to explain quite a bit. I think this will be 9. This is the greatest integer function, also known as the step function. And so this is the notation that's used with the greatest integer function, or the step function. So often we see this. And then the question, well, how is that defined? That's the important part, right? So this is equal to the greatest integer less than or equal to x. So yeah, we'll define it and then we'll show you what we mean by this in math. So this will output the greatest integer less than or equal to x. Okay, so let's make a chart so we can sort of understand how this works. So here's the input, and then the output will be the greatest integer of x. So I'm going to give myself a little bit of room here. So do the same. Let's start with 0. If I input 0, this wants to know, so if I input 0 here, what's the biggest integer less than or equal to 0? Well, that's 0. Let's try 0.5. If I plug in 0.5, this wants to know what's the largest integer that's less than or equal to 0.5? The or equal only comes into play if you input an integer. So if I input 0.5, what's the largest integer less than 0.5? 0. What if I input 0.92? What's the greatest integer less than 0.92? 0. What about 1? What's the greatest integer equal to 1? 1. So do you see what's happening here? If you input an integer, it outputs the same integer. If you input something that's not an integer, it essentially rounds down. (1.2). What's the greatest integer of 1.2? 1. 1.81 outputs 1. The greatest integer of 2, well, that's an integer. This function, if you input an integer, it outputs the same integer. What's the greatest integer of 2.9991? It rounds down. It wants to know the greatest integer less than 2.9991. 2. Greatest integer of 3 is 3. Greatest integer of pi is 3. Do you see how that works? Let's try some negatives now. Well, again, if I input an integer, it outputs the same integer. But let's suppose I input negative 1.4. What's the greatest integer that's less than negative 1.4? Negative 2. You see that? Negative 5.7. What's the greatest integer that's smaller than negative 5.7? Negative 6. Okay, so what does the graph of this function look like? Now you'll see why it's called the step function. Okay, so let's say I input 0. If I input 0, this will output 0 since 0 is an integer. But if I input any decimal between 0 and 1, this rounds down to the biggest integer less than that. So if I input 0.5, this outputs 0. So this is going to be open because as soon as I get to 1, this will output 1. See that jumps up or steps up? For any decimal between 1 and 2, this will round down to 1. I get arbitrarily close to 2. And then when I reach 2, this jumps up. The greatest integer of 2 is equal to 2. For any decimal between 2 and 3, this will round down to 2, arbitrarily close to 3. And then when I get to 3, this jumps up. For any decimal between 3 and 4, this will round down to 3. And I think you get the idea. And this keeps going step by step by step. Etc. So that is the step function. Where is this used in real life? If you think about how the post office works when you bring packages there to be mailed, for a certain up to a certain weight, they cost one flat rate, and then when you exceed a weight threshold, then they cost the package cost the next amount to ship it. So sometimes this is called the post office function. Domain is all real numbers. What about the range? What am I outputting? Do I output any number between here? It looks like I'm only outputting integers. So the range is actually the set of integers. And that is a classic step function. Okay, so the last thing we want to do is give sort of an algebraic test for symmetry. So we want to talk about these even and odd functions. Very, very important idea. Very useful for making calculations easier in the future as well. I think that's surprising as of right now, but you'll see that down the road. So let's give a definition. So we're going to say y equals f of x is said to be even in the understanding that this is a function. So y equals f of x, that's a function. It's said to be even if f of negative x equals f of x for every x in the domain of f. These functions, these even functions, they all have y-axis symmetry. Why does that make sense? Because notice that looking at symmetric places on the x-axis, x and negative x, the function takes them to the same y value, right? So say here's x, and symmetrically, say here's minus x. Well, if the function takes both of these to the same y value, then you can see that there's y-axis symmetry. Okay, so the next definition, which will be odd function, right? So suppose y equals f of x is a function. So y equals f of x is said to be odd if f of negative x equals negative f of x for every x in the domain of f. These functions have origin symmetry. And so the idea here is these symmetric places on the x-axis, so symmetric x's lead to, or opposite x's lead to opposite y's. So for example, here's x and negative x. Well, f of x is the negative of f of negative x. So you've got this origin symmetry. Oops. Pretend that has origin symmetry. There we go. I get the smiley face. My drawings are just fantastic. You know how lucky you are to get drawings of this quality? Look at that. Okay, so if we want to look at some examples of graphs, well, from our library, we've actually seen some of these. So the absolute value function, this is even, right? It has y-axis symmetry. This, is this Ralph? I think that's Ralph. Hey, it's Ralph, everybody. Ralph. So Ralph has y-axis symmetry. So both of these are even functions. And then this, the standard cubic function, this has origin symmetry. So that's an odd function. And this reciprocal function has origin symmetry. So it's also an odd function. But the question then becomes, well, how do we test for this algebraically? Well, the key is to just use the definition. So that's what we want to do. So I'm going to say So examples. So determine whether the following function is even, odd, or neither. And let's do this for 4 examples. Let's say f of x is equal to x cubed minus x. Let's try this for g of x is equal to 6x squared plus x to the 4th plus 3. Let's try this for f of x equals x squared times the square root of 1 minus x squared. And let's try this for about h of x equals x plus 2 over the square root of x squared plus 25. Okay, so yeah, let's try this out. So our first function, so we want to determine if this is odd, even, or neither. So we start off in the same way for either the even test or the odd test. It starts off with f of negative x. So what does f of negative x mean? It means, well, everywhere that the function has an x, I'm going to plug in negative x. Okay, so next I compute. What happens if I cube an odd number? It stays odd. I'm sorry. What happens if I cube a negative number? That gets a smiley face. So if I cube a negative number, it stays negative. And then here the double negatives will be positive. But it almost looks like the original. It's just negative 1 times the original. So let's factor out a negative. And then we realize that this is negative of x cubed minus x. But that's exactly negative f of x. That's the definition of an odd function. So I'll say, well, therefore, f of x equals x cubed minus x is an odd function and has origin symmetry. So you can see how this is quite powerful because I get strong symmetry insight without having to graph this. I mean, some of these would be very, very difficult to graph for now, and algebraically I can determine whether this has a type of symmetry or not. It's really, really nice. Okay, so let's try B. Odd, even, or neither? Let's find out. So the key is to use the definition. We start in the same way, whether we're testing odd or even. So we plug in negative x and see what happens. Okay, well, if I square that, that's just going to become 6x squared because it's an even power. That's an even power. So that'll just be x to the 4th. Nothing happens here. But that's the same thing as g of x. That's the definition of an even function. So therefore, g of x equals 6x squared plus x to the 4th plus 3 is an even function with, maybe that sounds a bit redundant, an even function with y-axis symmetry, but maybe that's fine for now. I just want you to connect those two. Okay, so let's try C. Okay, so to test, we plug in negative x. Okay, we carefully compute. Negative x quantity squared is x squared. And negative x quantity squared is x squared. But that's the same thing as f of x. And so f of x equals x squared times the square root of 1 minus x squared is an even function with y-axis symmetry. Okay, not so bad. And so lastly, h of x okay, so we test by plugging in negative x. Okay, we compute where we can. And we're just going to note a couple things. Well, that's not equal to the original h of x, right? So the first thing that I note is that h of minus x, that's not the same as the original h of x. So h of x is not even. So there's no y-axis symmetry. But I also note something else. If I try to factor out a negative, so suppose I did, that's not the same thing as negative h of x. Right? That's not the same thing as negative h of x because negative h of x would have both of these negative. So we also have that h of negative x is not negative h of x. So h of x is not odd. So there's no origin symmetry. And so this must be neither.